it's so close that I don't know if I would make too big of a deal about it.
Say marginally significant.
Could say something like that. We have some waffling languages like that in our field that we can pull out of the hat for a moment like this. But anyway, the point there was just to show you how with something as complex as a Latin square design, I can still use the means test to test for equal variance. How? Well, I focused on the main variable of interest, brand. And so I imagined the 4 brands, each having 4 observations. These would be the residuals, each having 4 residuals at those levels of the brand. And I wanted to test whether the variation in those 4 groups were equal or not. I wanted to use the means test. So this is how I can accomplish it. Okay. Questions on that? Anything more I should say?
As we did the means test before, the SAS doesn't throw off the zeros.
Yeah.
I know we're stuck with it.
I think we're stuck with that if we're going to use SAS. I would rather throw away the zeros. If I was doing the work by hand, I would throw away the zeros. But let's look at the data ones. The brand is all permuted here, so this is hard to see. Let's look at brand A, 0.125, 0.625, 0.375, and whoops, there's a little weird one, -1 something. So we have 4 residuals when brand is A. And since there's an even number, the median is going to be between the middle 2. So I guess I'm not going to get a 0 there, at least naturally.
Unless 2 are the same.
But unless 2 are the same, yes. Exactly. So maybe the problem of the 0 didn't worry us in this example, but it could on another day. And as far as what I can tell you, I would say, well, if we're stuck using SAS, we just have to accept that it's going to leave the zeros in there.
Okay.
Okay, so much for that. So, SAS program number 14, it says. Let's see what it's got in it. So we looked at this copper data before. Here it's coming up again. And we have input variables, temperature, copper, and then the warp is the response. So I guess copper is the amount of the copper additive in the material. Temperature seems plain. Warp is the response. So there's the data in those 3 columns. So I guess the purpose of this example would be to say, how do we do a 2-factor ANOVA with SAS? That's all that's going on here, nothing fancy. Let's see what we try. So print the data, proc GLM, class, temperature, copper, okay. Model, warp equals temperature, copper, temperature times copper. So notice how I put the interaction in the model line. Okay. Means on temperature, copper. Here's the combination being used. /T, least square means temperature, copper, temperature by copper /T diff. I'm not sure what I was doing here. I think I just wanted to see what would be the difference in the output for means versus least square means with these different slashes at the end. So let's see what happened here. There's a print of the data on the first page, and here's the ANOVA too much stuff, but let's look at the main part of it here. It's down at the bottom, say there. This one is not significant. This one is significant. This one is not significant. And again, I should have done those in the other order. I should have tested the interaction first to see whether I would go on and test the main effects. But anyway, the interaction is not significant, so I would turn to the test of the main effect and get those kind of results. Copper is significant, temperature is not. What is going on here? This is the variable. Oh, it says on the back of the previous page. It says what it's doing is doing t-tests for the variable warp, which is our response. And so this is just regular t-test, and apparently there's two levels here. Why is there two levels? I'm missing something. Oh, the first variable, temperature, has values 100 and 125. Two values for factor A, say. The second variable, copper, is 1, 2, 3, 4 levels. Okay, so that's why we have a 2 here. There's the two means based on 8 observations, and well, it tells us the temperature here, 125 versus 100, and then we get the same sort of thing on the other variable, copper, which in this layout right here is listed there. Copper values of 100, 80, 60, and 40. And there's the mean response there.
So what it's saying between those two T groupings is that there isn't a significant difference between temperatures, and there isn't a significant difference between the copper formula of 80 and 60. Is that what's going on?
Where are you seeing that conclusion?
I'm not, well, it's because of the letters there beside the T
Oh,
grouping.
you're looking at the letters over here.
Yeah,
All the A's.
That's your underlining?
That's the underlining method, right?
Okay.
And then when we come down here to the other variable, copper, we have A standing alone,
Right.
well, whichever one it was, it's the 100. Then for the B's, we would have 80 and 60 are apparently equal. And then the C is the third value for the last one. That's apparently different from the rest of them.
So that's how
So
we
yes,
interpret
you
this.
can interpret these letters here as our usual underlining method for what's equal and what isn't equal. That's handy to have. On the back page, this table at the top of the page seems to be a table of the cell means. So here's the value of the first variable, 100 or 125. Then the next column is the value for the second variable. That's 4, even though it's 4 again. The sample size in each cell is 2. These are the means. So these would be the means of the cells. And then this is the standard deviation in the last column. Okay, so we're not going to do anything with that here today, but notice that information is there for use another time. So then we're finishing up the GLM procedure with the t-test. Here's a t-test for comparing temperature 100 against temperature 125. There's the means, here's the t-value, and there's the p-value of the test. So accept H naught of equality there. That should be consistent with what we found back here with our underlining A. They're all under the same underline, both of them are under the same underline, so they're included to be equal. So that's apparent in this t-test here. Then we go on and look at the other variable, copper, which had 4 values. There's the means. And then here's the table involving the pairwise t-tests. Okay. So it says what it's done here. It's going to take the difference of the two means as the hypothesis of interest. And so when we look at this, we would say this one is significant, this one is significant, this one is significant, this one is significant, this one is significant. This is the only one which isn't significant right there. So it's a comparison between 2 and 3. 2 and 3 are 60 and 80. So looking at this table, there's only one comparison which is not significant. It's the comparison between copper of 60, copper of 80. Now if we look at the previous page, I think that's what we saw there as well. Yes, right here in this layout, look at the underlining here again. As far as the 4 levels of copper, there's copper of 80 and 60, which share a common line, so they're equal. And all the other pairwise comparisons do not share a common line, so they're different. So this layout here is consistent with the last page. Information is just being laid out in a different fashion. Questions on that? Anything more I should say about it?
The first part would be the means, the actual point estimates, whereas the ones on the back page are the standardized t values and their associated p values.
Yes.
Good.
All right, last stats today. All right, let's see what this is all about. This title basically says two-factor ANOVA. The data is from textbook, page 140. And here's the variables. Factor E is exhaust index. Factor V is pump voltage. And the response is tube pressure. So we have these 3 variables. And we're going to input them in this way. Okay? So I'm going to enter E, V, and just call it response, RESP for short. So those columns are the data. So this variable E has 1, 2, 3 levels. Variable V has 1, 2 levels. So this is a 3 by 2 table. It would look like this, where up here would be variable E with 3 levels, and in the rows it would be variable V with 2 levels, and then we have these 6 cells. And so there would be 2 observations per cell. So that's what the data looks like. So it's a very simple, short set of data. So how do we approach it here with SAS code? Well, class EV model, there's my response, equals E vertical bar V. Notice the new syntax here? It's just a little shorthand for giving me both main effects and the interaction between the two variables. If I had 3 variables in my problem, if I had a 3-factor ANOVA, I could do something like A vertical bar B vertical bar C in that model line. And what that's saying is, give me all 3 main effects, give me all 3 two-way interactions, and give me the 3-way interactions. So this is just a shorthand way of asking for that information without typing all those terms out on the SAS code. So then I ask for means and least square means, and let's see what comes out of that. Then I'm noticing what I'm going to do here. I forgot something that was back up here, excuse me. It's this line right here. So I'm defining a new variable by this equation. Cell, I'm calling it. And basically, it's going to be 2 times E minus 1. Here's my picture again. E is 1, 2, 3. And V is 1 and 2. So if I have 2 times E minus 1 plus V, that's cell 1. Then I take 2 times E minus 1, E is 2. So that's 2 times 1 is 2, plus V, which is 1. Wait, what am I doing? I guess that's a 3. Where did the 2 go? Down here?
It's down there.
Let's check down here. So down here, E is 1. So if I let E be 1, that whole first term drops out, and V is 2. So yes, 2 is down here. So anyway, I had to think about that equation a little bit, and what it effectively does is to label the cells 1, 2, 3, 4, 5, 6. So instead of typing this in the columns here, I let the program calculate this variable cell by that formula. So that's my trick. Then when I come down here, what I have is a proc GLM itself least square means. Then I have another proc GLM where I'm going to use this new variable cell. here's the model equation, only the cell. And then here's the line for the Levine's test. Okay, then there's another prop GLM down here. What's that going to do? Class EV, response E times B. That's the same thing as up in my first GLM. So what's different? I guess the least square means is different. And what I've done here is to put the product first. Whereas up in the first one, I didn't do that. So what I'm trying to get at here is pairwise comparison of the cell means. Let's see what happens. So first of all, print the data. Then the ANOVA table. Interaction is significant, so I don't really care about the other two tests, but I can peek and see that E is and E isn't significant if I wanted to look at that. But significant interaction between E and B. So when we look at this underlining procedure for factor E, here's the levels of E, 1, 2, 3. Here's the underlining business, A, B, C. So there's nothing in common in the underlining, so they're all different. Then we come to V, which only has 2 levels. And with the underlining procedure, we see they're both under the same underline, so we have that done. They're equal. Now we get some different looks at the output. Here's the 6 cells broken down by level of E and D. Sample size of 2 in each cell. Here's the means, here's the standard deviations, and maybe we could look at it here in this layout here. 1 and 2 different. 1 and 3 different. 2 and 3 different. So all are different by these pairwise t-tests. Then this is getting kind of redundant now. Here's a t-test about comparing the 2 levels of V. There's the t-value and corresponding p-value of that t-test. So it's not significant. Now what I'm doing here, notice, is to look at the variable E times V. E times V is the joint variable. So notice there are 6 levels of E times V. There they are listed right there, and then they are the rows of this layout as well. And so what I'm doing here in this layout is to say, go back to the vision of the data this way and do a pairwise comparison of one cell against another. I can do cell 1 against cell 2, cell 1 against cell 3, cell 1 against cell 4, etc. So there's all those combinations. Pairwise comparisons of one cell against another cell. That's what's going on in here, and it continues down here as well. So we could look at which ones are significant, some are, and which some aren't. I don't think we need to stress that here in class. So we can see some of those comparisons are significant, others are not. So that's this layout right here. How did I get that to come out again with my command? Remember what was done there with it? That was where we did what?
Oh, it's just,
I guess it's sort of redundant here. It's maybe coming out from this line here because there's an E times V in there, or maybe it's coming from this last GLM and there's an E times V there. I think both of them produce the same table. Yes, the very last output here printed is that same 6x6 pairwise comparison business that we had looked at just a moment ago. So that was redundant in my commands. Okay, so a few different ideas came up in there.
Excuse me.
Yes.
So when we test for E times V is the same when we test for the cell.
Say that again, Judith.
So when we introduce this cell variable, then when we test for differences between the cells, does it say for testing for E times V? Because E times V is the interaction. No? My question is that why does it say that the LSU squares for the effect E times V when we don't test here the interaction but the cell?
Well, in one context, E times V is an interaction. In another context, it's just a way of referring to the joint cells.
So there's no use for the cell, for defining this cell variable, no?
Well, where did I use it? I used it only here in this middle GLM so that you could see what was going on. And the way I used it was only use it to did as well. And so they're not doing Levine's test anyway. So the only place where the cell variable was used was in this middle GLM to run Levine's test. It's in the output here somewhere, now I can't find it. Here it is. Well, that's interesting. If you look on, whatever page it is for you, 1, 2, 3, 2, 4, 6, back to page 6. Here, when it's trying to do the Brown and Forsyth test about homogeneity and variance, notice that it's a bust. You can't do anything. Well, why? Well, there's two observations in each cell. The median would be halfway in between them, right? So when we take the absolute value of the difference from the median, both those numbers are the same. So when I come to run this Levine test, the two numbers in each cell are identical. The two numbers in the first cell are identical, the two numbers in the second cell are identical, and so forth down the line. So when we try to calculate any kind of variation, there's none. And that's why we're getting this junk here, when it's trying to run Levine's test, because it can't do it.
And can I have a look?
Sure.
That here, because we have interaction, we move from interaction to check the effects because the p-value was smaller or was small enough. What's the difference between this and the home assignment? Because at the home assignment, you said that after we saw that we have interaction, we don't check for factor effects. But we check it because the p-value is small.
Well,
Do I get it right? Or-
no, I think what I maybe was doing was misleading you a little bit. When we find a significant interaction, officially we don't bother to test the main effects. It's hard not to look at them because they're right there in front of your eye, right? So it's hard not to see them. But basically, just cross that out and say, well, when there's significant interaction, we're not interested in the results of testing the main effects. That's it. I guess what I'm after is on, in your handout, it would be on page 4. The number in the upper corner is a 6. But anyway, I have these numbers here. So what they're telling me is that when E is 1 and V is 1, what I'm trying to do is make a graph. Which way do I want to do it? I want to put the variable E down here. 1, 2, 3. So when E is 1 and V is 1, it's 53. Let me get some sort of a scale here. 50 is maybe there. 40, 30, 20, 10. Let's try that. So when E is 1 and V is 1, I'm at 53. And now I'm going to go when E is 2 and V is 1, I'm at 30.5. And then when E is 3 and V is 1, I'm at 11. So let me plot those points and label that V equals 1. Now, when V is 2, E is 1, V is 2, it's a 58, so it's up there. Then it's a 12, which drops way down to there. Then it's a 7.5, which drops down yet a little bit further there. So label that trace V equals 2. Now, my point here is meant to be a simple one. We found there's significant interaction. So what do? Pack up our pencils and go home? There's something more to say. We might be interested in saying, well, what's the effect of E and B jointly on the response? So for example, these look fairly close. Is that amount of difference statistically significant? Run a t-test on that. This difference here, is that statistically significant or not? This difference here, is that statistically significant or not? So anyway, you could look at a graph like this and come up with, say, 3 anyway, maybe more. But you could come up with 3 comparisons that would be this way. You could maybe say, maybe I should run a Tukey or Bonferroni type confidence interval because I'm looking at this simultaneously. So I should use one of the simultaneous methods for doing this. But anyway, having drawn the graph, finding this interaction you're seeing here insignificant, gives us an idea as to what we might do on a next step. And let me just introduce it briefly here as far as what's going on. We want to talk about nested experiments, whatever that means. Take a look at this example 1. Here we have factor A is a fungicide spray on fruit trees. Factor B is a tree. And we have 10 orange trees to use in the experiment. So we've got 10 orange trees, and each tree is going to get one of the sprays. That's the only practical way to do it. You can't take a given tree and spray it with 3 different fungicides. You don't know the effect of the fungicides if you don't do that. So the layout here is telling us what's going on. There are 10 trees. Tree 1, tree 2, up through tree 10. And there they are planted in a row or something like that. And we have to decide how we're going to spray these trees with the fungicide that we have. And we have 5 different types of fungicides. So apparently we have to say 2 trees are going to get fungicide 1, 2 trees are going to get fungicide 2, to keep it balanced. Okay, so we'll do it in a balanced way. So the way this is laid out, it's saying spray 1 goes on tree 1 and 2, spray 2 goes on trees 3 and 4, and then spray 3, spray 4, and spray 5. Now as this is laid out in front of your eyes, it looks like the trees are there in a row, and then we're going to spray these 2 on the end with fungicide 1, and then move over and spray the next 2 with fungicide 2, and so forth. That's not what's done. We randomize the choice of fungicide to the tree. So somewhere it probably says that here. Yeah, decided at random. So which tree gets which fungicide is randomized. So although you see it looking like this in front of your eye, this isn't the way it happened. You wouldn't want to do the experiment in such an organized way. So notice that point. And then it says, well, what are we going to do once we've sprayed these trees? Well, we want to see whether their leaves are protected. And so instead, we're going to, after some time, take 3 leaves from each tree. And so there's 1, 2, 3. And measure some kind of response on the leaf. So from each tree, we get 3 leaves. And so we're going to get data like this. We've got 10 columns, 3 rows. We're going to have 30 observations in this data set, right? Now, there's two factors going on in this example. One is the fungicide type, and the other is the tree. We would probably think that the fungicide is a fixed factor, and the tree would be naturally a random factor, because we're not interested in these 10 trees so much as they are just representative of trees. So one of the factors is fixed, the other is random. But there's more going on here as well. The layout of the data would be, excuse me, one factor is spray, it has 5 levels. The other factor is tree, it has 10 levels. And so that starts to give us this impression of this 10 by 5 matrix of observations, but that's not what we have. This is what we would have if the two factors were what we call crossed. These two factors in this example are what we call nested. So we say that tree is nested in spray. We want to test about differences in the sprays and also for differences in the trees. So we have two goals about what we want to test about, both of these factors. But the two factors are not crossed, they're nested. What does nested mean? Well, look at the example and it sort of pops right out to your eye. What does it mean to say that tree is nested in spray? Each tree gets one and only one spray. Each tree gets one and only one spray. So when we have data that's nested like this, our issues in this handout are going to be how do we do some standard statistical things like confidence intervals, tests of hypotheses, and so forth. What's the same? What changes when we have nested experiments? Well, we don't have time to get into it today. Let's take this up on Thursday as our topic of that day. So bring this back with you again on Thursday, and we'll continue there.